Now, say we take our virtual flight and we go in Asia. We go in Asia. We are ready to start as a session in South Korea. And I welcome with me all the guests that are joining to talk about the strict relations between the farm and the fork, talking about
Hello.
sustainability within the food system. Good morning, everyone. Welcome on board
Good afternoon.
this journey. Good afternoon. Good morning for me. And welcome in the Food for Earth Day Marathon. So the Food and Agriculture Organization of the United Nations, together with the Future Food Institute, today are celebrating with all of you the Earth. So happy birthday, Earth. And we are very happy to celebrate the Earth also touching South Korea. So in this panel, in this session, we're going to talk about sustainability from farm to fork. This is one of the biggest challenges. We need to fix the food system, starting really to shortening this connection and making all the steps of the food chain more sustainable. So let's start about what's the perspective and which are the challenges you are facing. And I want to introduce the first speaker joining us today, talking about transbounding water, energy, food nexus. When we talk about food and energy, and all the issues related to this link, there are many things that we can tackle and we can really do to fix the food system. So I want to talk first of all with Professor Lee. Welcome on stage.
Thank you very much, Sarah. Can you hear my voice clearly?
Very well.
Thank you for inviting me to this session. It's a really great session, and happy to Earth Day. Actually, I didn't expect I'm the first speaker of this session because maybe I look at the other speakers and I prepare this somewhat things. Anyhow, I'm gonna start my presentation. Can I share my screen?
Of course, yes. Of course, yes.
Okay.
Share your screen. And we are really interested about really today investigating about which are really the relationship between all the different steps in the food chain, because we know that everything is connected. So I think the presentation works and you can start.
Okay. So can you see my presentations?
Perfectly.
Right? Yeah, today I'm gonna talk about some transboundary food security based on the water and food nexus. Sarah mentioned there are a lot of things including the water and food nexus system, but the main question, actually this topic starts from the one main question is like who or what are responsible for the food security. I'm working at Chungbuk National University in South Korea. My name is Sang-Hyunhee. I'm gonna start my presentations. Okay, let me start about some water and food nexus and its boundaries. I mean, everyone admit each resource like food or water or energy are really connected by human activity. For example, irrigation water supply, maybe it's like connection between the water and food. And I think the human activities make this ring boundary of each resource, but also connected, the boundary is expanded. So we need to really understand what is the interlinkage between the food, water, energy in order to achieve the more sustainable food security under climate change and the social economic change situations. So this is some simple case study about some transponder impact in the food security. I think the achieving the food security is really important in South Korea. I mean, we have only 27 self-sufficiency ratio of the grain crops, but we have 100% self-sufficiency of the rice. That means rice is really, really important food crop in South Korea. And then we really need to keep that high level food security of rice for future. But we need to understand if you want increase or if you want to keep high level of the food security, you need to secure other resources like water supply, water resource, or energy resource, or land resource as well. So I want to analyze the impact of food security on other resources, like in terms of transboundary the analysis using system dynamics modeling, and I quantified in the future, 2030, if we reach it to 100% of food security of rice, how much water we also need, how much energy or how much land also we need, and in addition, how much carbon will be emitted by the energy consumption for food productions. So I don't want to say food security really need energy or other reasons. I want to say we need consider how to secure other resources for achieving food security in the futures. Another transboundary impact in food security is climate change. In these days, we understand that climate change affects many variables, many relationships. In this study, I'm more focusing on climate change impact on relationship between food and waters, like water footprint, also food and land, like food footprint, like how much water, how much land will be required for food productions. And we simulated how much water footprint and also land footprint in the future season from 2020 to 2100 using climate change scenarios. And then we found that so really much of the irrigation water we need for food security in the future, especially in drought seasons. And another point is about resource boundary in terms of food security or in terms of water and food relationship nexus. Traditionally, the water management really consider physical transboundary, like watershed, how much water from the watershed to food producing areas, like the left part in these figures. In these days, many research apply the water footprint or virtual water concept, which means embedded research in the food products. So they quantify or analyze the virtual water trade, like embedded water trade in food trade. So that means virtual water flow from food producing area to food demanding areas, like or food exporting country to food importing countries. So in this case study, I want to quantify, okay, how much from watershed to food demanding areas in terms of physical water and virtual water flow. So first, we quantified how much virtual water from main rice producing area to metropolitan area, like Seoul is capital city in the South Korea, or Incheon, Daegu, or Busan is the biggest cities in the South Korea. So we found that the really much of the water resource in the Jeollanam-do area is southwest area. Actually, they use water for the rice productions. But that means we can convert that means to a lot of water virtually used by the people living in metropolitan city by food consumptions. So I want to say the food security is not the issue in food producing area. It's also issue for the food consuming areas. And we really understand not only food production, but also water or energy support for food securities. And today, in this year, I extended our case study from the South Korea to Japan and also global scale as well, and quantify how much water flow from each water basin to food producing area is physical water, like irrigation water, It's like real water. And we quantified how much virtual water from producing area to consuming area. Finally, we quantified from the water flow from water basin to consuming area, and we analyzed how the change of the food security affect the physical virtual water flow from basin to consuming areas. Okay, and based on this case study about transboundary impact or transboundary of the water resource or transboundary of the food security, we want to make this kind of some transboundary management system based on based on the water energy nexus system. But first, we should understand the boundary of each resource we call watershed, energy shed, and food shed. Actually, the watershed is based on the physical boundary, like a real water supply, water base, that kind of things. We already analyzed many things about watershed. Energy shed is more like the some electricity powered network system based on the power plant and consuming areas. The food shed is like more tricky things. I mean, food is a more tradable product, so we should consider not only producing area but also consuming area. So how to combine this producing and consuming area as a food shed. Based on this kind of analysis of water energy food shed, we want to apply that kind of the characteristic of the resource boundary into the system dynamics to assess the holistic impact in terms of a new transboundary concept. I mean, new transboundary means not only physical boundary, but also virtual boundary of the water, energy, and food. So this is the conclusions. Transboundary management that I mentioned in this slide include the interlinkages among the resources, water and food boundary combining virtual and physical water, and new perspective of transboundary combining resource shed, water, energy, and food shed. But still, we have a lot of challenges. I mean, we need this kind of nexus platform to apply our concept or our research into the real world policies. And also, we really need to consider how the value of the resources. I mean, in South Korea, agricultural water, irrigation water is like a free of charge. But if we consider economic impact of the food security with the other resources, we really need to understand the value of the water or value of the land, other resources. And last challenge is sustainability. Food security is not a short-term problem, it's more long-term task. So we really understand, we really prepared some supporting system, the system for supporting the food security in the future and the climate change impact as well. So I believe my research about some transboundary, including not only food production, but also water supply, energy supply, and also multi-stakeholder, not only farmer, but also consumers. I think that kind of some involving these kind of some boundary or stakeholder could be essential drivers for more sustainable and resilient food security in the future. Thank you very much. My presentation is the end of this. Thank you, Sarah. Hello?
Hello? Here we are. I'm back. Thank you so much. I think through your presentation, we've been really understanding what's the connection between all the linkage that are connecting the topic of energy and the food system. And this is really something in which we have to focus on. Today is Earth Day, and we know that the world resources are not endless. And so we need really to be focused on preserving all the resources we have available nowadays. I think it's really interesting, the starting point.
Yeah, thank you. Yeah, of course, yes, I really agree with your opinion. I mean, we really need to understand that some relationship between the water and food and energy and food for achieving the more sustainable food securities. But there are a lot of tasks. I mean, a lot of scientific report, many things. So we need to look.
Definitely, yes. And the topic of water is for sure one of the main focuses also on this marathon. We have been exploring how in different parts of the world this is becoming also a big issue. In many different parts of the world, there is also a huge risk of desertification in the next years ahead. So, of course, water is life, and we need to be all aware about that. Thank you so much, Professor Lee. And let's really jump into this journey around South Korea. And now I would love always to stay within this area and involve Phil Jo Kim. I hope I spelled in the right way your name.
Yes, Phil Jo.
Okay. Today, I'm going to learn many different languages, more than 30 countries. Thank you so much
You're so happy.
helping me. Exactly. Oh, I need to be happy. Today is an important day.
Yes.
So thank you so much for joining this journey. And really, we would love also to learn from you another peel of lesson, always being focused on this topic.
Okay. Thank you so much, Sarah. And can I present my topic?
Of course, yes. Because now, after water, we need to talk about the soil. We need to talk about all the issues that are connecting soil and carbon.
Oh, yeah, you can see my the PPT.
Yes.
Okay, I will start my presentation. Because I am soil scientist, I am always studying soil carbon because soil is very important as a carbon sink. Today, just I will talk what is the soil carbon, what is the real target to management of the soil carbon. My name is Pilju. Please call me simply PJ Kim. I am professor at Gyeongsang National University in southern part of South Korea. And as you know, we are living under the global warming stage. We are suffering from very high concentration of the carbon dioxide atmosphere. This is one of the analyses. In the atmosphere, approximately 750 gigatons of the carbon present at carbon dioxide. However, in the land terrestrial, more than 9 or 8 times higher carbon is accumulated in the land. For example, in the soil, 2 times bigger than the atmosphere, approximately 1,500 gigatons carbon in accumulated as organic carbon in surface soil. Also, vegetation, like a plant, have the similar levels of the carbon, similar with the atmosphere. This meaning in the agricultural sector, such as the surface soil and the plant management could be very important practice to control atmosphere carbon dioxide, as well as global warming. This is a very simple background because after human stage, we developed the field, agricultural field, from the rainforest or some the natural ecosystem. Natural ecosystem, they have the very high concentration of the organic carbon. This meaning the carbon dioxide, deeply sequestrated in the inner soil. However, after developing land, cropping land, lots of the organic carbon degraded into carbon dioxide. This meaning also agricultural sector is very important, the greenhouse emission, and we contribute the global warming. And now we need more some clever soil management practice, like to increase soil organic carbon stock to mitigate global warming. We call this is the conservative soil management. This meaning very simply, one of the soil management practice to increase soil carbon stock. We call this is carbon sequestration. Simply, we can dispatch some background to the soil carbon balance in the agricultural ecosystem. This carbon balance is one of the differences between carbon input and output. Using this like balance, we can estimate how much carbon accumulated in a soil or depleted in a soil. For example, the balance such as there are same input and same output. In case of this one, soil carbon stock change was not changed. However, in our agricultural sector, we are enjoyed always higher input than output. This meaning resulted in deplete of soil organic carbon. And this level of the organic carbon also emitted into atmosphere as the methane as well as carbon dioxide. However, in the future, for the sustainability, we need more higher input organic carbon and then increase soil organic carbon stock. This increase also can contribute the decrease of carbon dioxide concentration in the atmosphere. There are so many methodologies can increase the soil carbon stock. Depending on your condition, you can select the best one, can increase soil carbon stock in your condition, like conservation tillage, winter cover cropping, soil fertility management, elimination of the summer fallow, like something. There are so many methodologies proposed. However, depending on your condition. 지금 돼? Okay. Sorry, the PPT something problem, and it's okay. There are so many methodologies. We can select best one. However, in the rice paddy always flooded by water. In case of this one, different story there are, because the carbon dioxide, soil organic matter generally coming from the carbon dioxide via photosynthesis. In the case of this one, also on aerobic condition, this is can go into carbon dioxide. In case of this one, there are no problem. However, under the flooded condition, on aerobic condition, like rice paddy, this is converted into methane. In this case, a different meaning in the global warming. As you know, this is the greenhouse gases, such as the carbon dioxide, methane, or nitrous oxide. All is coming from the agricultural sector. However, methane is very interesting greenhouse gases, more than 23 times bigger than carbon dioxide. We have the global warming potential, meaning one molecule carbon dioxide only have the global warming potential. However, one molecule of the methane can contribute 23 times bigger than carbon dioxide on global warming. This is one of the typical patterns of the methane emission in rice paddy. Like during the winter season, we call this is dried soil condition. There are the very small levels of the methane is emitted here. However, for rice cultivation, we are irrigated and flooded the soil. After that, lots of the greenhouse gas, like some methane, is emitted from here. And then in particular, some with adding higher organic matter, such as barley, hairy vetch mixture, dramatically increase the methane emission. This is the negative effect. Our target was to increase the soil organic carbon via biomass addition or organic matter source addition. In rice paddy, however, this is make another factor. This is increase high the methane emission and then become more seriously global warming. There are so many methodologies proposed because this is coming from the lack of the oxygen in the soil. We are trying to increase oxygen concentration in the soil by something tillage management, no tillage or minimum tillage. Also, water management could be very clever management strategy, because this is coming from water irrigation problem. And then controlling water level, we can improve the oxygen concentration in the soil and then decrease the methane emission. Also, organic matter, such as very stable organic matter, like the compost or biochar, could be very important, the agricultural practice to decrease methane emission from the agricultural sector. In the future, in my expectation, fertilization management could be one of the new way, very wise way to decrease methane emission, such as addition with some specific or non-specific inhibitor. Might be we can develop new technology can reduce the methane emission from rice paddy. Also, one of the important point, rice cultivar, there are so different characteristics, also make the so different methane emission as well. In here, one of the example I will show the mid-season drainage. This meaning the only water management. During the rice cultivation, just we quit irrigation for 30 days. However, comparing with the continuous flooding, this meaning not quitting irrigation, this mid-season drainage dramatically decreased methane emission during rice cultivation. Under any condition, irrespective with any condition of biomass addition, this simple mid-season drainage practice can decrease methane emission more than 40% of the total flux. My topic is finished here, and I want to introduce my symposium, the 8th International Symposium on Soil Organic Matter. This symposium will be held the next year, June 27 to June 30, and in Seoul. Please coming here, we will discuss this greenhouse gas as well as soil organic matter. Okay, thank you so much.
So thank you so much. And we've been touching, I think, the crucial elements: soil, carbon, water, all the elements that we need to preserve when we talk about the connection between food production and the health of the planet. Thank you so much, Professor Kim. I think that now we have to go and talk very quickly because we are running out of time, but we have to focus on agriculture because we have really to start to connect the dots and talking about the sustainable agricultural practices, it's crucial. So please, Professor Jeon, join us.
Hello, can you hear my voice clearly?
Very well.
Oh, thank you. Yeah, it is my honor to present my research topic. Today I'm talking about nature-derived crop stimulant for sustainable agriculture. Actually, as you know, we have used much amount of chemical NPK fertilizer and intensive method to increase crop productivity, but we have found there are several disadvantages about this technology. For example, generally chemical NPK fertilizer show low nutrient use efficiency. As a result, much amount of excessive nutrients has been released into the environment, causing eutrophication, and many land is suffering from acidification also, and the irrigation and the tillage method also cause salinization or organic matter decomposition, thus causing low crop productivity. Actually, these things indicate we need more sustainable agriculture method and more eco-friendly materials to increase crop productivity. So today I would like to introduce natural derived material, humic substances. Actually, humic substances are soil organics, and this material can function as many different things, such as microbial respiration and pollutant transformation and heavy metal movement. But importantly, this soil organic can facilitate plant growth because they can act as a soil conditioning agent. And recently, many scientists have found that these materials can directly stimulate the plants, thus increasing their crop productivity. So actually, humic substances are widespread in nature, but in the agriculture sector, we generally use a high amount of humic substances. So we generally use coal-derived humic substances. But the problem is, the distribution of coals biased, and some nations doesn't have any coal resources to extract humic substances for agriculture. So today I would like to introduce how we can make humic-like materials from plant-derived materials per agriculture. So you can see this table. Actually, this leonardite or humate, it's core-related materials. We can extract a high amount of humic substances from these core materials, but it's biased over the world. So actually, if you focus on how humic substances derived from plant materials, you can easily recognize plant-derived polymer materials would act as core materials for producing humic substances. So if we focus on plant-derived materials, we may change plant-derived polymeric materials into humic-like materials. So I'm now focusing on technical lignin. Actually, these lignin materials are plant-derived renewable materials, and it's actually bio-waste from biorefinery and paper manufacturing processes. So if you focus on lignin structures, and if we focus on humic substance structure, you may easily recognize these two materials are quite similar. But you can also observe that there are some differences. So if we modify lignin material with the proper method, we may obtain humic materials for sustainable agriculture. So this table shows which portion of lignin structures are different with the humic substances. So, for example, N contents or oxygen-based functional groups are much more widespread in real humic substances. So we need to introduce such functional groups into plant lignin, and then we may obtain humic-like materials for sustainable agricultural practices. So I have developed two kinds of method. First is a top-down method and the bottom-up method using lignin materials. A top-down method is just breaking down the lignin material into small molecular weight lignin variant, and then you can also introduce oxygen-based functional groups and nitrogen-based functional groups. And the second strategy is the bottom-up method. Using lignin-derived small phenolic compounds, you can make polymerized materials. So you can synthesize polymer materials mimicking humic substances. Through this way, we can synthesize humic-like materials to treat crops or farmland to increase crop productivity. So you can see the real effect of my strategies. So this is a top-down method. When we use lignin variant, you can see more enhanced crop productivity appear like this. And then we can also apply bottom-up method to synthesize humic-like polymeric materials. You can see more enhanced germination property, and then actually this material also can give some abiotic stress resistance to plants. So this is a high salt of sodium chloride, but in the presence of humic-like materials, plants can resist such harmful stresses. And then also leaf area or root growth can be enhanced in the presence of humic-like materials. So my message in this presentation, we can use eco-friendly and alternative crop stimulants by using natural derived materials. If we use such material instead of chemical fertilizers, we may perform some more sustainable agriculture practice. Thanks for listening my presentation. Yeah.
So thank you so much. And what you have been sharing is really inspiring us to push forward and invest more in developing climate smart solution for the farming system.
Yeah.
And the reducing chemicals is crucial to preserve the health of the soil everywhere in the world. I'm super inspired by the lessons we have been hearing from our friends in Korea, and I need to thank all the scientists working hard to fixing the issues within the food system and bridging the gap between farm and fork with sustainable solutions. And I have to thank so much also the Italian embassy in Seoul and Ambassador Della Seta for the big help and the connection with the academics and all the researchers in South Korea that are working hard really to make a more sustainable food system. Thank you so much.